Our today's lecture is on layers of protection analysis. In short, we call this as LOPA. We will see some safety systems that we use in our process safety in order to ensure the safe operations. Safety systems are layers of protection. If you recall from our previous accident modeling lectures, if we have any hazards, it gets converted into an accident when it passes too many barriers. If you recall the Swiss cheese modeling particularly, so this is the barrier failure, this is the barrier failure, this is the barrier failure, which converts these hazards into an accident. One thing you need to keep in mind as we are moving forward to this course, hazard is something that can cause harm. For example, it could be chemicals, electricity, or even the water spill on the floor, snow on the road nowadays especially. Whereas risk is the chance that any hazard will eventually cause harm. Usually it is taken as low, medium, or high. If there are no chances that the hazard will not cause any harm, it is not considered as a risk. For example, let me give you an example, very simple example. So this is a room, okay, and there are two entries into this room. This is my door number 1, this is my door number 2. For example, there was a water spill on the floor on door number 1. This is an hazard because it can cause you harm. There is a possibility that you can get slip through this water on the floor. So there is a risk associated with this. However, if you are not using this door number 1 at all, every one of you is using door number 2 to enter into the class, so then there is no risk associated with it. Why? Because we are not going to in contact, or we're not going to deal with this hazard at all. Okay. Second thing, this chance is technically what is called as the probability. Once we will go into the risk lectures more detail, you will see that we will work on these probabilities values. So risk is a chance that any hazard will eventually cause harm. It could be low, medium, or high. Depending upon the situations, we can also take very high risk. For example, oil and gas industries, they do have their high risk values, but if we look on some nuclear power plants, they might have very high risk value as well. Folks, safety systems are the layers of protection. It is the protection of our system from unsafe event. So hazard by themselves do not lead to hazardous events. As I just explained you, the difference between risk and the hazard. A combination of the triggering effect, that is an isolated incident, or a combination of them lead a hazard to develop into an accident. Safety systems are the layers of protection to prevent a hazard from leading into an accident. This one we will explore more as we go into this chapter. Folks, safety is ensured through automation. Automation is required when equipment, control, and operators may fail. Multiple failures may occur. Automation is required for quick, timely, and well-defined action. We will see today how the automation can take actions in a very timely way and in a well-defined action in order to ensure the safety of our system. So let me give you a very simple example of the tank. This is the tank which has, let's say, water in it. It is filled with the water. I have the water input which is being regulated through a valve. It is called control valve or funnel control element as well. And I do have an exit of the water from the tank. So this is my input of water line and this is my output. In order to control or maintain the water flow into this tank, we use some instrumentation and process control. And these are those control system. This LT is your level transmitter. This is the pneumatic transmission. For those of you who have electrical background and chemical background might be able to understand it well. And this is my level controller, this is my input output, and these are my electrical signal. So what is happening in this system, as soon as the level transmitter detects the level of the water, for example, this is the set point for the water level, it gives a signal to the level controller that the water has achieved a certain level, and this level controller through the instrumentation, it controls the final control element and give it a signal to close it. So this final control element will be closed by our instrumentation. So this is a very simple example of process control and instrumentation system. I will repeat it one more time. So we have the level transmitter here. It detects what is the specific set level of the water. For example, you want to have a water level of let's say 2 feet. So as soon as the 2 feet level water is reached, this level transmitter will give a signal to the level controller, which will ultimately close this valve because the water level has been achieved. Again, if the level is less than the set point of the 2 feet, it will give a signal to the level controller. Level controller will open the valve so that the more water can come into the tank and we can achieve a level of 2 feet. So this is very simple example of instrumentation and process control on a system. This system, we can also use it on our output line. We don't have to use it on our input. Folks, is this clear to everyone? Or if you have any questions about this, because I need to build up my next lecture on all of this. Okay, thank you. So the basic process control system, BPCS, are implemented for safe operation. Now this is what we called as our first layer of protection, which is a control, basic process control. Now the question is, either this control is enough to ensure the safety or not. And the answer is no, this is not enough. So this is my first layer, which is the basic control, process control. Why it is not enough? What if the control mechanism fails? The warm liquid temperature is too high. Now full opening of the cooling valve is not enough, or it's not possible. May need to shut down the feed valves. It required the operator intervention. Now, how do the operators know when to intervene? That is the next questions comes in our basic control system. This is where we introduced our alert system or the alarm system, which acts as our next layer of the protections, and it alerts the operator by warning the operator that system is going out of the control. For example, as I was taking an example here, so for example, this level, which we set at the height of the 2 feet, it is at 2.1. or 2.5, which is a dangerous now because the water can overflow from our system. So that's where the alarms will go off and they will warn the operator that we need an operator intervention. Now, is this really enough that operator can intervene, or there could be the failure of the operator? My next question comes, what will happen if operators fail to intervene in a timely manner? Operator is a human being. We can expect some errors from the operators. So what if the operator fails to take the corrective actions? The reaction can go run away, the temperature can increase sharply, not enough time for operator. This is important point here. Operator may not have enough time to take the corrective action. It requires to stop the feed flow. So we need to shut down the feed flow automatically. So we need to have a mechanism which can automatically shut down our feed flow or the input into our process. That is where our next layer of the protection comes, which is the safety instrumented system. In short, we call it as SIS. So what is the basic objective of safety instrumented system? We place it to automate our emergency actions. We want a system to take its own action in case of any emergency. Instead of operator intervene, the system should have the ability to take the corrective actions. It activates when the critical process variable exceeds the specified limits. As I just might give you example, for example, the level was 2.1 or 2.5 or any level higher than the set point, it will intervene and activates on its own. It is automatic and no operator action is required. So because it is an automatic system, we can expect to have it work in a very timely manner and take the decision. Before I go into this, let me explain something here. Now, what was our basic objective again? We have a process. We want to ensure the safety of this process. In our example, we are taking the filling of the tank. So our first layer was the basic process control. The second layer was the alarms. And the third layer is safety instrumented system. One thing you must notice that in order to ensure these protection layers, we want them to work in parallel, not in series. Because if they will work in series, the failure of one can lead to the failure of the rest of the layers. You will see some more layers are coming on the top of this. So we do not want that. So this next slide is mentioning that your safety instrumented systems should be independent of the control system. For example, this is my system here. This is my system here. Let's forget about this one. I will come back to this point here. This again, we have the water going into our heat valve, heating system, and we are getting the steam here. So all these controls are being measured. The fuel level is being measured through this control element. But when we included our SIS, safety instrumented system, we also installed some other in parallel systems which can control it instead of adding them into series. Because we want our safety instrumentation system to be an independent of the control system so that the SIS system can take an action without intervening our other control systems. Now, when the closing and opening of the valve is not enough, so the pressure goes beyond the limit, opening the valve could not be possible, may be unsafe for the following equipment and need the quick release. So this is my system that we were referring before. We have the input valve here and we have the output of the water flow. Let's say our safety instrumentation system is not able to control the action. So what could be the next step? we need to have some relief devices. This is the instrumentation symbol that we use for the relief device. So we need to have some relief device that can release the material out of our system so that it can safely shut down. And this thing is what introduces our next layer of protection for our process, which is called as a physical protection or a relief devices. So relief devices are the last preventive layer. It provides an exit path for fluids, normally used to prevent unusually high pressure that may cause vessels or pipes to burst when we have the danger of bursting of our vessels, resulting from large disturbance or equipment or the power failure. It is designed to be activated when control and sys are not enough. This is what I also explain you. We want our protection layer independent of each other. So when control and sys are not enough, the relief devices will help us to ensure the safety of our process. So the release is done in a controlled manner. So we started with our process. First, we try to make our process inherently safe design. The next step was we maintain the variable at the desired values, which was through basic process control system. Our third layer was the alarm system here, which warn about the abnormal situations. And the safety instrumented system was the next one. This is our SIS. It shut down the part of the process if it is not safe to do so, if it is not safe to operate. And so far, our next layer is the relief devices, which diverts the material safely. 4 independent layers of protections. Let me do this. This is 1, this is 2, this is 3, and this is 4. Now, what happens when the relief devices are not enough even? What to do if all the preventive layers fails and the material and energy is released? The basic definition of the risk as two component, it is the product of your probability and the consequences. Probability is what I was referring you here as a chances. So far we will controlling our probability using the preventive layers, which reduce the probability or the chances of an unsafe event. However, we have exceeded this limit. Now the next phase we enter is that we will have some consequences because the material has been released so far from the relief device. And that's what where we can control the consequences. Okay, so I will repeat it one more time. We have so far with the relief devices, the material has been released. Now the only thing that we can do is we can control the consequences. We can reduce the consequences. This is what happens when you get a fire. So with the fire eruption, you try to control the spread of that fire. Technically, you are trying to control the consequences of that fire. So can we do something to reduce the consequences? The answer is yes. So in case of the release of the material and energy, consequences should be reduced. Either we can use some dikes which contain the material, or we can go with the emergency managements. It could be the plant procedure, or it could be a community response. So this was our layers of protection system so far. My next will be the physical protection, the dikes. So here, from here to onward, I'm trying to control the consequences. Just remember the equation of the risk, which is the product of your probability times your consequences. So here I'm trying to, from this to top, I'm trying to reduce my consequences. Or it could be a plant emergency response, or it could be a community response. I just shared in our, I think, second lecture, I shared you an example of MGPI plant. If you recall that video, that investigation of the accident, there was a community emergency response that was taken in order to ensure that at least the community is safe through the consequences of this disaster. So these ones that we were using for our consequences control, these are called as our mitigating layers. However, anything from relief valve up to the basic control system is what we have the preventive layers by the control system. So this is my plant design, and this is my first layer of the protection, which is the process control. And then I apply my safety control system, which is the alarm system, instrumentation system, and relief devices. Since the material has been released at this point into the atmosphere, we try to reduce our consequences of that damage. It will involve the containment of the material in the dikes, which is the physical devices, or it could be the plant emergency response, and it could be a community emergency response. So again, what is the basic objective? That we can reduce the risk. Our first layer, it helped to reduce some risk. The second layer helped to reduce some risk. Safety instrumented system helped to reduce our risk. Mechanical relief valve helped to reduce our risk. And the last was the containment of the material helped to reduce our risk. We try to keep doing this until we reach our residual risk. So each layer of protection should be independent. To be considered as an independent protection layer, a system should meet the following criteria. The first is the specificity. An IPL is capable of detecting and preventing or mitigating the consequences of specified hazardous events. Independence, its performance is not affected by the failure of another layer. Its performance is not affected by the conditions that caused another layer to fail. The protection layer is independent of the initiating causes. Dependability, it reduces the identified risk by a non-specified amount, and audibility, it is designed to permit regular periodic validation of the protective functions. This one is more in our reliability engineering related thing. So out of all these layers, our detailed work in your course is based on SIS, which is the Safety Instrumented System. Safety instrumented systems are designed to respond to the condition of the plant, which may be hazardous in themselves, or if no action were taken, could eventually give rise to a hazardous event. They must generate the correct output to prevent or mitigate the hazardous events. Folks, these are some of the standards associated with the safety instrumented system. I will share you a document which has some notes related to them. You can have a look on them. So this is the basic definition, that safety instrumented systems are designed to respond to the condition of the plant, which may be hazardous. Now, what is included in a SIS, safety instrumented system? It is composed of some sensors. It is composed of a logic solver and the final element. This is also called final control element, and it is usually a valve. which I just showed you in my basic process control. So safety instrumented systems are used to implement one or more safety instrumented functions. This is abbreviated as SIF. One thing I want to make sure you don't get confused with SIS and SIF. So I made some couple of more slides so that I can explain you the difference, and I will try to understand you what is the difference between SIF and the SIS. So instrumented system used to implement one or more safety instrumented function. So SIS are being used to implement SIF. A SIS will automatically taking a process to a safe state. That's what we were required. If you recall our diagram for the instrumented system, this is our basic system, and we want, if operator is not able to intervene, we want our SIS to be activated automatically taking a process to a safe state when specified conditions are violated, permit a process to move forward in a safe manner when specified conditions allows. And that's what we call as a permissive function. Taking action to mitigate the consequences of an industrial hazard. It will take action in order to mitigate the consequences of an industrial hazards. Be responsible for the shutdown functions and consequence reduction of the functions. All these functions have a common attribute that they all reduce risk. So what is our main aim of SIS is to reduce our risk. Now safety function with a specified safety integrity level which is necessary to achieve the safe functional safety. In our SIF, which is the safety instrumented function, there is a calculations or the method through which we identified our SIF. That is what we called as a safety integrity level, SIL. Again, this is the definition from this standard, but understanding them is more important, which I will elaborate in my next few slides. Safety instrumented function. It is a set of the equipment intended to reduce the risk due to a specific hazard. It includes the elements that detect an accident is imminent. It decides to take action and then carry out the action needed to bring the process to a safe state. So the safety instrumented function, it will detect if an accident is imminent. It will take an action, and then it will carry out the action that is needed to bring the process to a safety level. Now, for some example of a safety instrumented function, for example, open coolant flow valve to prevent the column rupture due to over temperature. So in this function, we are concerned about the temperature only. So this action is being taken in order to control the temperature. So function is related to some variable. It could be temperature, pressure control, volume control into the system, and so on. This is important slide. If you understand this, it will be easy for you to understand the difference between a SIS and a SIF. So SIF refers to the single function. As I just mentioned, it could be related to pressure, or it could be related to temperature, or the shutdown, low level shutdown. Here we are controlling our level. So a SIF refers to a single function. Okay, let me write it down here. So it could be a temperature, or it could be your pressure control, or it could be your level control or volume control, and so on. However, the SIS is refers to all the combined functions that make up the overall system. So I can say that a sys will have more than one SIF into it. In terms of the SIF, most SIFs contain a single input sensor and a single or possibly a few final elements. However, when we are talking about a SIS, which is a system, safety instrumented system, it can have more than one or dozens of or hundreds or even thousands of input and outputs, because this is representing a system. Safety instrument integrity level is what we used for a SIF, not a SIS. It is the ability of a SIF to detect, decide, and act is designated by the safety integrity level of the function. One determines the SIL safety integrity level for each safety instrumented function. It is incorrect to refer a SIL to an entire process or unit. Okay, this is very important. When you are talking about SIF, safety instrumented function, we identify what is its level. It is same like a unit of a SIF in a very layman language. We identify what is the level of our safety instrumented function in terms of our SIL. There are 4 levels basically, 1, 2, 3, 4. So one more time, I will repeat it myself. Your safety instrumented function is represented using safety integrity level. This is just kind of a unit for, let's say, temperature as a unit of Kelvin and so on. However, we cannot define our SIL for a whole system, which becomes a safety instrumented system. So it is incorrect to refer to the SIL of an entire process unit or the piece of the equipment. To what extent can a process be expected to perform safely? This is what we learn from our SIL. This question is answered to assignment of a target safety integrity level. We will work on some numericals and see what is the target safety integrity level. SILs are the measures of the safety risk of the given process, or SIL is the measure of the system safety performance. Again, this is associated with a function, not a system. So when we say integrity, it means the state of being unimpaired or undamaged, state of being entire and complete. So safety integrity is expressed as the probability that the safety related system will satisfactorily perform the required function. So when I say the function, then immediately one thing it should come to your mind. It could be any variable, temperature, pressure, volume, etc. Under all stated conditions within a stated period of time when required to do so. That is when our demand occurs. That's what is the safety integrity. We express it in terms of the probabilities. So as I mentioned your SIL has the 4 level. It is level 1, 2, 3, and 4. SIL 4 has the highest level of the safety integrity, whereas the level 1 has the lowest level of the safety integrity. And we can go intermediate between 2 and 3 if we require to. If system is not safe at level 1, we will see through our numericals how we identified this SIL. Then we move to our next level of the safety. If we identify that system is still not safe using level 2, we move to the level 3 and so on. If the system is not safe at level 3, we move to the level 4. That is the highest safety integrity that we can provide to the system. As I mentioned you, there are some standards available which are used to determine the SIL level into a SIL level of a SIF. There are quantitative methods and there are some qualitative methods, which include the risk graph and the development of the risk matrix. First method is the ALARP, which is as low as reasonably practicable. The idea hinges on 3 overall risk level. It could be unacceptable, tolerable, broadly acceptable. This one is mostly coming from UK. Not a direct method for determining SIL, however, the idea can be used. So when we say ALARP in safety and risk engineering, it meant to say that we have this kind of the triangle. At the bottom of the triangle, we have the risk, which is completely negligible. However, at the top of this one, we have the risk which cannot be justified. This is completely unacceptable risk level. So we want our system to operate between these two extreme regions, and that's what we call as the ALARP, or tolerable region. So we have the negligible risk and we have the maximum unacceptable risk. We try to operate between this region. We try to operate our system between this region. Second method is the risk matrix method, which is based on evaluating the risk in a very qualitative way. So we have the 5 level of the risk, and each level has a specific definition. For example, this is my frequency of the hazard. For example, if I say at level 5, so what could be the word that it can be frequently occurring? And the definition at the level 5 hazard frequency is a failure can be reasonably be expected to occur more than once within a specified lifetime of the plant. However, when we go to the level 4, we can see some linearity. So a failure that can reasonably be expected to occur within a expected lifetime of the plant. So this is how we define our all 5 levels for frequency. The same procedure we repeat for our severity level. So we have 5 levels of the severity. It could be the catastrophic, severe, serious, minor, and the negligible, depending upon what are the losses. So in case of the catastrophic, we take as the multiple fatalities. In case of the severe, we take as a single fatality. All these are qualitative terms. It can vary from industry to industry. As you can see, in terms of the negligible hazard severity, we only need some first aid treatment. So this is the basic shape of a risk matrix. We have the severity levels here, level 1, 2, 3, 4, 5, and we have the frequency 1, 2, 3, 4, 5. We develop our risk matrix, and then we identify what is the low risk associated, what is the medium risk associated, and what is the high risk associated with this. How we do that? So this is my severity levels 5, 4, 3, 2, 1, and this is my frequency 1, 2, 3, 4, 5. How do you fill this matrix? Because this is a risk matrix. As I mentioned you, the risk will be your product of your probability, which is the frequency, time the consequences, which is the severity level. So means to say, if I want to fill up this point over here, it will be the product of 5 times 1, which is 5. If I want to fill up this one, it will be 5 times 2, which is 10, 5 times 3, which is 15, 20, 25, and so on. This is how you fill up the rest of your cells here. Once we have identified our risk matrix using these numbers, then we identify what is our criteria for being a low risk, medium, and the high risk. For example, a company identified that the low risk level is between 1 and 4. So any number which are considering 1 up to 4, it is categorized as a low risk. So let me change this color and I can explain it better maybe. So we go to our risk metric, and from 1 to 4, any number which is associated with this is also coming into this. This is region is what we identify as a low risk, because the numbers are coming between our range of low risk. In terms of high risk, medium risk, sorry. Let's change this to something else. In terms of the medium risk, which is coming from 5 to 9, so I can have this region. I'm not including 12 because it is out of my 9 range for the medium risk level. Okay. This is what is identifying me my medium risk level. This region. In the qualitative terms, usually we don't write the numbers, but we identify them using the colors. But how do you decide where colors should come? This is the way that we work in our risk matrix. For our last one, let's take it as a green. So any risk which is 10 or greater, it's the high risk. So as we can see that all these regions, they are coming, they have the value which is more than 10, other 10 or more than 10, that is what we classified as a high risk level in a risk matrix. Okay, so we have the low risk, we have the medium risk, we have a high risk. As I mentioned, usually you don't see the numbers in the risk matrix because it's a qualitative matrix. But again, how do you decide about the location of a specific color? If you don't have the numbers here, for example, you may include it into the green, which according to our criteria will be wrong, of course. So again, this is another way to represent this. It is a qualitative matrix. I took it from some books, and in this particular example, they are taking the high risk up to this area. Okay, and this is my low risk here. And anything in between the high and the low is categorized as a medium risk. Folks, I will stop it here, and next time we will do some class activity on this safety risk matrix procedure more. And there is one more method that we need to work on. Do you have any questions for me?